Hey guys, welcome back. In the first lecture, we saw how recursion works, right? It creates the stack frames and then starts executing the stuff from the top of the stack. All of the frames wait for the result returned by the previous calls, right? And we also discussed what are the drawbacks of recursion. All we talked till now was about regular recursion. But there is another kind of recursion that is as efficient as iteration. Yes, and it is called tail call recursion. And in compiler terms, we also call it tail call optimization. Let's go ahead and discuss what is it. You all know how recursive programs works internally. For instance, how the recursive program of finding factorial of a given number behaves internally, right? An activation frame or stack frame gets created on each recursive call. Now these frames waits for the value returned by the previous frame so that it can calculate the right value for the current frame and again pass it down, right? So this is regular recursion. Now let's write the same code in slightly different way. See this code here. We are calling this function tail fact recursively. There are two input parameters to this tail fact. One is n, and the second one, which is an extra parameter, it's called accumulator. So this is a tail recursive code. Let's see what happens in this case. Let's say for the first call, the value of n is 4. So it again calls itself with n minus 1, which becomes 3, and n multiplied by a, which is 4 multiplied by 1, which is 4. So here completes the first call. Now notice it's not having any further operation to perform on the value returned by the next call. So it does not have any value to hold in this stack frame. So now it doesn't have to come back to this call and this frame can be removed. Now the second call, for this call n becomes 3. So it again call itself with n minus 1, which is 2, and accumulator, which is n multiplied by a. In last execution, the accumulator was 4, so this time it becomes 3 multiplied by 4. So the new accumulator is now 12, for n equals to 3. Again, it does not have to come back to this call, and this frame can be removed. Now the third call happens for n equals to 2. Again, it calls itself with new n minus 1, which is 2 minus 1, that is 1, and the new accumulator n multiplied by a, which is 24 because n is 2 and a by previous call was 12. And now with the next call, the frame is removed. Now the fourth and the last call where we have the if condition or the base condition where the value of n is 1. So in this case, it directly returned the accumulator passed to it. So hope you got the difference. In case of regular recursion or head recursion, it keeps holding on to the stack because there are further operations to be performed. So when the input is large, such recursion can result to stack overflow error. Whereas in case of tail recursion, we are having an accumulator to store the product in it. It's not holding on to the stack for the operations. That's why during each call, there was only one frame shown in the stack in case of tail recursion. In modern compilers like compilers of Scala, Kotlin, etc., tail recursive calls are converted into pure iteration or imperative loops at compile time to optimize the code. So this is the advantage of using tail recursion that you don't have with regular recursion, because compilers can't convert regular recursion into iteration. However, every recursion cannot be written in tail recursive way. But for any problem, if you can figure out the tail recursive code, you must go with that one. So this was all about tail recursion or tail call optimization.